Hi everybody, and welcome to the video on rational exponents. In this video we're going to talk about four objectives, and our first objective is how do we rewrite the nth root of a. Alright, so again, from our reading, again, please be sure to take the appropriate amount of time and be sure to review your textbook. But let's just note that we can rewrite from a radical form to what we call a rational exponent form. And this, by definition, is rewritten as a to the 1 over n power. So the idea is that the square root of x, I can rewrite this in as a fraction or a rational exponent as x to the 1/2. Again, remember from our previous discussion that the index here is applied to be 2. So we can rewrite the third root of x as x to the 1/3 power. All right, so this is something that we're going to do quite a bit of, and I guess, I don't know if hate, that's kind of a strong word, but for those of you that may be moving on to calculus, you will use rational exponents a lot. But they do come in convenient, and they do come in a little bit handy. So again, the idea is when we take a look at the 10th root of x, again, this is just x to the 1/10 power. And again, we can rewrite from the rational exponent form, say x to the 1/7 form, just to note that this is the 7th root of x. Okay? So we have things like 36 to the 1/2 power can be rewritten as the square root of 36, which we can go ahead and evaluate and say that that is equal to 6. We have the 1,000 raised to the 1/3 power, which we can re-express as the cubed root of 1,000, which we know is going to be 10. And let's just take a look at the form negative 64 raised to the 1/2 power. Again, let's just recall that in this form, the base is 64. The negative does not tag along, so this can be re-expressed as minus the square root of 64, which we know is going to be negative 8. And let's just compare and contrast that to, say, negative 25 raised to the 1/2 power. And note, if I rewrite this, this would be the square root of negative 25, and we know that this is does not exist in the real realm. So this is not a real number. Okay, so let's just make sure that we're careful of this notation. And finally, we could take a look at, say, 125 x to the 9th power raised to, say, the 1/3 power. And we can note that this is just going to be the cubed root of 125 x to the 9th power, which by previous discussion, we know we can rewrite this or actually compute this as 5x to the 6th power. Let's just note that we'll take the cubed root of 125, which we know is 5, and by previous discussion, the cubed root of x to the 9th. Remember, this is just 9 divided by 3. Okay, and we'll see this a little bit later as to why this is the case. So our first objective, so basically objective 1 then, is just to note that the nth root of a is a raised to the 1 over n power. Our second objective takes more of a generalized view. So the second objective is to note that the nth root of a base a raised to the m power, well, we can rewrite this in its rational exponent as a to the m over n power. Okay, so we can note that in this case that 7 to the 2/3 power, again, just using this formula here, using this equivalent way of rewriting, is that this is equal to the cubed root of 7 squared, or the cubed root, if you will, of 49. Okay. Let's see. For computation purposes, though, I just want to point out that a lot of times, so for the most part, to evaluate a to the m over n power, it's a lot easier to note that this is going to equal to the nth root of a. Sometimes it's easier to compute that part first and then raise this, your final result, to the mth power. So let's just note, for example, if I wanted to evaluate 16 raised to the 3/2 power, let's just note that this can be rewritten as the square root of 16. We can use that denominator of the fraction first, raised to the 3rd power. And it's easy to note that the square root of 16 is 4, so this is 4 cubed, so this evaluates to 64. Whereas if we were to take a look at the square root of 16 cubed, then we have to take 16 and cube it, and we get this huge number, this really, really huge number. And then you got to try to figure out what the square root of that number is. So for computation purposes, hopefully you can easily see that this one is a lot easier to compute this way. Let's take a look at negative 81 raised to the 3/4 power. And again, let's note that this is exactly the same way as writing negative 81 to the 3/4 power. Because note that, again, 81 is what's raised to the exponent. It has nothing to do with the exponent. And again, we can compare and contrast that to the difference between this guy and this guy to the 3/4 power. So this one's, again, is not a real number, so it does not exist, all right, because we can't take the 4th root of a negative number. So let's just note that this would be the 4th root of negative 81, and then we'll take that and cube it. But remember, we don't take even roots of negative numbers. So let's just note that this, in this way, then becomes negative the cubed root. Now, the 4th root, the 4th root of 81, and then we'll take this whole thing. Actually, we'll take this whole thing and cube that. So we know that the 4th root of 81, again, you can take these numbers and multiply them by themselves. This is going to be 3 to the 3rd power, and notice this is negative 27. So this evaluates to negative 27 here at the end of the day. And if we got something, say, for example, 2x raised to the 3/5 power, again, the only thing we can do is rewrite this as the 5th root of 2x raised to the 3rd power. Okay, and that will take care of that. So again, this is the objective 2 then. So this is objective 2. So the bottom line is to write this general form right here. And that is to note that objective 2, I'll rewrite it down here a little cleaner, says that the nth root of a to the m is a to the m over n. And so let's just note that this equality does go back and forth. All right, so let's take a look at objective 3. Objective 3 then is with negative exponent. So remember, when we had something like a to the minus 2 power, we just rewrite this as 1 over a to the second power. So the idea is that with negative exponents, we end up putting things back into the denominator and making the exponent positive. And we'll do the same thing here. So let's just note that a to the minus m over n is just 1 over a to the m over n. And we know that this can be re-expressed as 1 over the nth root of a to the m power. And then for evaluation purposes, it's easier to go ahead and do 1 over the nth root of a raised to the m power. Okay, let's take a look at a few examples here. So let's just note that we have 9 to the minus 3 halves power, which is, say, 1 over 9 to the minus 3 halves power. Oops, no minus there. Thank you, I caught that. And note that this is just 1 over the square root of 9. And again, since we want to do this cubed, which ends up being 1 over 3 cubed, which is 1 over 27. And again, let's take a look at negative 64 raised to the minus 2/3 power. Rewrite this with its positive exponent. We get 1 over negative 64 raised to the 2/3 power. And note that this base is negative, but we're taking a cubed root. So we get 1 over the cubed root of negative 64. All right, and then this is going to end up being squared. And we note that this is 1 over negative 4 squared, which is 1 over 16. Okay. So the negative exponents, we've seen these quite a bit before. All right, and it's just write them in their denominator and go ahead and just take care of business. So our last objective is the rules of exponents. So I would like to just put out to you a note that on page 607, there is a number of rules regarding exponents. So you've seen these before, probably a long time ago when you had whole numbers and so forth. So let's just go over these things really quick. So the idea is that if we have like bases, we get a to the m, a to the nth power. And the interesting thing is this rule says that we add the exponents together. So if I had 3 squared times 3 to the 5th power, then this just boils down to 3 to the 7th power. Our next rule says that if we take a, raise that to a power, and then raise it to another power, then this rule says that we just product the exponents. So we get a to the m times n. So for example, if we had 3 to the 4th power and we wanted to take that to the 3rd power, this just becomes 3 raised to the 12th power to use that rule. The next one says if we have 2 unlike bases, a, b, and raise them to the mth power, and again, it doesn't matter if m and n are positive, are whole numbers or fraction numbers, this is going to work. So this becomes a to the m, b to the m power. So for example, if I had 3x to the 3rd power, then using this rule, I get 3 to the 3rd power, x to the 3rd power, so I get 27 x to the 3rd power. And if we have a fraction, a over b to the mth power, then this is a to the mth power, b to the mth power. And again, notice here that the bases are all different. So for example, if I had 2/3 to the 3rd power, then I'm saying that this is going to be 2 to the 3rd, 3 to the 3rd, which is 8 over 27. Okay. Again, going back to like bases, Okay, so if we have a to the nth power divided by a to the nth power, then we're going to have a to the m minus n. We kind of used this rule earlier when we were dividing a polynomial by a monomial. So we were implied using this. We just kind of did a little shortcut around that. So note that if we had a to the 6th power and a to the 4th power, then this is a to the 6 minus 4, which is a squared. Or if we had a to the 5th power divided by a to the 7th power, then I get a to the 5 minus 7, which is a to the minus 2 power. And again, using our negative exponents, it's 1 over the a to the 2nd power. So just to give you a hint, all right, we always write the final result, always write positive exponents. Just to go ahead and throw that out. So we also know that anything raised to the 0 power is always equal to 1. So it doesn't matter if it's 3x to the 0. This is equal to 1. It doesn't matter if it's the square root of 2x squared plus 3, and all of that is raised to the 0 power. This is still equal to 1. And again, our final rule, which we've already visited, is negative exponents. We just rewrite those as a 1 over a to the n. So let's take a look at these with rational exponents, some examples. So we get y to the 2/3 times y to the 8/3. And let's just know that by our rule, we have like bases, so we add the exponents. So y to the 2/3 plus 8/3, which is y to the 10/3. And this does not reduce, so we can go ahead and stop. Let's note that we have x to the 3/5 times x to the 1/4, which is equal to x. So again, we have like bases, so we add the exponents. So I get 3/5 plus 1/4. And let's just note that to add exponents, we have to have like bases. So if we take a look at the 5 and the 4, we note that the common denominator here is going to be 20. So I have to come over here and multiply by 4 over 4, and that's going to give me a 12 plus, and then over here we have to multiply 5 over 5, so that's going to give me plus 5. So this is equal to x to the 17 over 20 power, and that does not further reduce. So let's take a look at 9 to the 2 over 7th power divided by 9 to the 9 over 7th power. And again, because we have the ratio here, like bases, so we have a 9 as our base, so we get 9 to the 2/7 minus 9/7. So we get 9. And notice that since these fractions up top are already a common denominator, so we get to the negative 7 over 7, which is 9 to the negative 1, which is 1 over 9. Again, we rewrite our final answers with positive exponents. So this is a standing rule. The standing rule says we always write final answers with positive exponents. Okay, this is a big time rule here. All right, so let's bring together a couple of these rules kind of all together here. All right, so let's see. Let's take a look at 3x to the 1/4, y to the minus 2/3. We're going to raise that all to the 4th power, divided by x to the 4th y. All right, so here we got a few things going on, so we're going to have to, let's go ahead And notice that we have this raised to an exponent, this raised to the exponent. So we already know we're going to have to use a rule, and in particular, we're going to go ahead and implement this rule right here that says when we have these different bases raised to the exponent, we're going to go ahead and rewrite using that rule right there. So let's just note that this can be rewritten as 3 to the 4th x to the 1/4 raised to the 4th power and y to the minus 2/3 raised to the 4th power divided by x to the 4th y. Nothing happens down here to the denominator. So let's take a look at this right here. So I have a base to an exponent to an exponent. So let's scroll back up here. So now we know that when we have a base to an exponent, we know we're going to go ahead and multiply those exponents together. So scroll back down here. 3 to the 4th, there's nothing to do. So you can either keep that as 3 to the 4th or rewrite that as 81. So this is going to be x. So 1/4 times 4. And then we get y to the minus 2/3 times 4 divided by x to the 4th y. Okay, so I'm just doing this step by step. So if some of you get kind of the mental math, I get it. You know, you could probably ditch a step. All right. So here we get 81. So we're almost done. So notice that 1/4 times 4 is x to the 1st power. And then here we get y. So 2/3 times 4 is to the minus 8/3 divided by x to the 4th y. It's x to the 4th y. And notice that this x will cancel with this and turn that into a 3. So we get 81 y to the minus 8/3 divided by x cubed y. And so our last step then is to note that we get 81 y to the minus 8/3 minus 1 divided by x to the minus 3. And this is 81. So notice that 3 can be rewritten, or this 1 can be rewritten as 3 over 3. So I get negative 8 minus 3. So I get minus 11/3 divided by, and I got a minus there for some strange reason, so x/3. So again, last step, rewriting with positive exponents. Again, we get 81 divided by x cubed y to the minus 11/3, or sorry, y to the 11/3, and there's nothing else more that we can do with that. Okay. All right. So let's take a look at, well, let's do one more example. So m squared n raised to the 1/2 power divided by m to the negative 1/2 n to the 5/8. Okay. So again, here we'll use that rule that says this is m squared raised to the 1/2 power n to the 1/2 power divided by m to the minus 1/2 power n to the 5/8 power. Okay, so this is going to be m to the 1 power n to the 1/2 power m to the minus 1/2 power n to the 5/8 power. So let's work with the m's. I'm going to do the m's first. So notice this is m to the 1/2. So if it's negative down here, I'm just going to bring it to the top and make it positive. Oh, let's just do them both. N to the 1/2 minus 5/8 power. So notice here that this is m to the 2 over 2. So that's m to the 1, because I got to add the exponents. So I end up with m to the 3/2 power and y. So notice here we got to get a common denominator. I'm sure we can agree that the common denominator is 8, so we get 4 over 4. So notice I get 4 minus 5 divided by 8. So we get m to the 3/2 power y. And let's see, looks like we get y. So 4 minus 5 is negative 1/8 power. So here we get m to the 3/2 power divided by y to the 1/8 power. All right, so that would be our final answer. But just to go one step further, just in case, let's just note that this is the square root of m cubed divided by the 8th root of n, just to have one more example to put it back into radical format. So, all right, so that's the video. And if you have any muddy points or need to see or talk about anything on any of these examples, or if you do happen to note a mistake, please let me know in the warm-up underneath the muddy points. So outside of that, I hope this video helps you out. We'll see you in class.